keynote speaker will be delivered by Professor Cynthia Dwyer of the John A. Morrison School of Engineering and Applied Sciences at Harvard University, and also the laureate of the 2026 JapanPrize for her landmark work on differential privacy and algorithmic fairness. Established in 1981, the JapanPrize honors researchers whose outstanding achievements have advanced science and technology and contributed to the peace and prosperity of humankind. Since 1985, the award has been conferred annually in the presence of Their Majesties the Emperor and Empress of Japan. Her keynote speech today is entitled, "There's a Science for That, AI, Responsibility and Choice." So please join me in welcoming Professor Dwyer to the stage.
Thank you very much. It's an honor to be here. Thank you very much, Consul General Takahashi, for the warm introduction. And I want to talk to you about a particular topic, which is privacy-preserving operations on data, learning from data. But I also want to sort of step back and frame the more general field. So as AI technology advances at an essentially inconceivable rate, we have choices to make, and we can make them. We can scale the technology responsibly or irresponsibly. We can offer privacy and stewardship or breach and theft. We can offer dignity versus degradation. These better values are not out of reach. A technology as powerful as the one we're building can perforce incorporate them. And science to do so already exists. So theoretical computer science, my field, is actually an excellent vehicle for introducing societal values into computation. So you can do math for social good. And inspired by conversations with the philosopher Helen Dissenbaum, who worked at the time, was creating a theory of what's called contextual integrity. How do you have privacy in public when there are surveillance cameras everywhere? I talked with Dissenbaum at the dawn of kind of the big data era, and I became really excited about trying to work on privacy from a mathematical perspective. And the key insight was actually a definition of privacy. And once we had that definition, many magical things followed from it directly. To this day, there's no competing theory for private data analysis, and together with successful work in computer science, algorithms, and engineering, this has led to widespread deployment both in industry and in the government. Okay, so let's move to learning from data. Okay. So this is a sort of a cartoon image of learning from data. All of modern AI involves extracting patterns from data. You can think of a learning algorithm as a function or a program that takes as input data of all kinds of types and produces some kind of an object. So it can also make random choices. So algorithms can learn from medical data, they can learn from social data, news, Wikipedia pages, music, art, code, an email corpus, the US law, movies, and all of these above simultaneously. So a natural question is, can my data even be detected? So here's this image, right? The function works on the data, it produces an output. Can my data be detected if I was in the input? So So this is obviously possible if it simply spits out some of the data that it was given, all right, without modification. Alternatively, it might output, say, Google Translate. So what's the problem with that? Well, in an example from 2018 showed that Google Translate could be tricked into spitting out some of the data on which it was trained. So here it is spitting out things from the Bible. Now, programs, the reason this happens is that programs such as Google Translate are trained on an enormous amount of data in many different languages. So, so it just repeated what it had learned. Can similar things still happen? What about with ChatGPT? The answer is yes. Similar things can happen even with ChatGPT, as a paper from 2023 showed us. So, not only does information sort of flow through the program, but information flows in our world in very mysterious ways. So this was another example. Consider public outputs of a recommender systems. So item similarity lists or recommendations of the form, which you probably have seen on Amazon. People who bought this book also bought that book. So consider those lists that change, or those recommendations that change over time. So if we combine information about what you have purchased, maybe because you actually posted about it on Instagram or on TikTok, if we combine information like that with these recommender systems, somebody could learn about a purchase that you made that you did not decide to post about. You made your private purchase and you made your public purchase. You blog about, you publicly talk about your public purchase, and the system says, oh, people who did that also want this private thing. So that was a problem. Okay. So suppose we say, let's make the problem simpler. Let's just give statistics. No fancy words, no language models, no recommendations. What if we just focus on statistics? Well, we'll only, say, give counts or fractions. So it turns out that even this is problematic. And a really dramatic example of this that was published in 2008 led the National Institutes of Health to ban publication of nucleotide frequency statistics obtained in genome-wide association studies that they fund. The policy has relaxed a little bit, but it still now reflects this caution. So let me just give you a little bit of background to see what scared the NIH so much. If you take any two people in this room, your DNA and my DNA, they're going to be identical almost everywhere. But there are places in the DNA sequence where there's large variation in the population. So maybe 95% of the people have a CC in this location, and 5% have CT, this minor allele, this variation. And so in a genome-wide association study, the genomes of members of a case group, say people who were diagnosed with type 1 diabetes, are compared with the genomes in the healthy control group, looking for a location in the DNA where the frequency of this unusual variant is very different between the case group and the control group. So we're just publishing a bunch of statistics. Well, it turns out that if you get hold of the DNA from somebody who was in the study, let's say from a glass of water that they drank, you can tell whether they were in the study or not. Amazingly, just from these numbers and their DNA. So it's not even just noticing that their genome suggests that they might get type 1 diabetes. It says that they've actually been diagnosed with type 1 diabetes, and that is a medical privacy compromise. Okay. So this phenomenon is captured by what we call the fundamental law of information recovery. We'll get to it. of information recovered with the data reconstruction theorem. And what it says is that if I give you overly accurate estimates of too many statistics, it will completely destroy the privacy of the people in your data set. And no matter how you attempt to blunt this attack by adding noise in order to hide individual presences, there's still just a hard limit on the number of measurements between privacies destroyed. And that limit is tied to the accuracy of the measurements. So you can think of privacy leakage as damage that happens because of radiation. And you can safely be exposed to more dental x-rays than you can to mammograms because the dosage is so different. So what's going on here is that it's very analogous to what you learned about in high school algebra. If I give you one equation and two unknowns, you really don't know anything about the unknowns. But if I give you a second equation with the same unknowns, then you can learn absolutely everything. And that is the fundamental law of data reconstruction. Okay. So where are we? Still thinking about statistics. A statistic is a quantity that's computed from a sample. It's supposed to tell us something about the population as a whole. Two data sets, both collected with proper sampling methodology, should tell us the same thing. This is why the field of statistics works. If everything that you learned from your sample depended really in detail on the sample, then you're not learning anything about the population. You're learning only about the sample. So our sense of privacy is derived from exactly this fact. Nobody knows I was in the sample. It might have been from a different sample. I could have opted out, and so on. So our intuition is that statistics feel private. We know they're not. We saw that from the genome-wide association study example. But it feels like it should work. And I want to say that this intuition is on the right track, but it needs some help. Okay. So, what should we mean when we say privacy-preserving learning? So, for the second time this morning, we're going to talk about Shohei Ohtani. So, suppose that Shohei Ohtani is part of a data set that contains useful and sensitive information, and we want to permit a data analyst or a scientist or you, the public, to analyze the data without compromising the privacy of the members. So what kind of guarantee would we like to make to Ohtani? A natural candidate, and one that I certainly started with, is articulated by the statistician Tordelinius in 1977. And it says that the data analyst shouldn't learn anything new about Ohtani. He may be a very public person and publish things about himself on the web and so on, and it's fine for us to know that. But the data analyst interacting with the private medical data of a hospital, for example, shouldn't learn anything new about Shohei Ohtani that they didn't know before. So that seems like a great definition. The problem is, it defeats science. So what is the point of a data set? Suppose I'm from Mars. I believe that all humans have two left feet. And in particular, I believe that Shohei Ohtani has two left feet. And we do a scientific study. We do a medical study. And we learn that almost all humans have one left foot and one right foot. So, my belief about Shohei Ohtani has changed. Right? I used to think he had two left feet, and now I think it's really likely that he has one left foot and one right foot. Has his privacy been compromised? Have I damaged him? What do you think? Hands. How many people think his privacy is compromised? Do you think it's compromised? No. Okay. How many think it wasn't compromised? Okay. Well, we're mostly in agreement on this. And it's a decision. We make a decision that we're not going to consider this a privacy compromise. Ideally, the same things would have been learned Johnny had opted out, right? So, and they would be learned even if he had opted out. So in that sense, it's not about him, it's about humans as a whole. So that actually brings us to the English language definition of what's called differential privacy, which is the mathematical definition that we'll work with. And we will see the one equation in a moment. So the English language definition says simply that the outcome of anything that is being built from data should be essentially the same, independent of whether any individual or small groups of individuals opts in or opts out. You're building essentially the same thing with something with the same properties, independent of whether any single individual or small group of individuals is in or out. Okay? And here's the formal definition. Oh, sorry, I should have said, when we say likely, where is this likelihood coming from? Our algorithms will flip coins. Okay. So this has been reformatted by the Museum of Science. Here's the idea. We have a data set X, maybe all of the people in this room, you're in data set X. And then we have a data set Y that is just like X, except one person has been removed. Okay? So you are in X, and one of you is not in X, is not in Y, it's only in X. And what this equation says is that the probability of observing any output is essentially the same, whether the data set is Y or if it's X. And this essentially the same is captured by that e to the epsilon, which is about 1 plus epsilon, which is a parameter that we control. You can make epsilon small and have better privacy. You can make it big and have better accuracy. This is the trade-off. Okay. So in particular, let's say you don't worry about whether somebody learns about your flossing habits if you're not in the data set. So if you are not in the data set, this is data set Y, it's not going to say much about your flossing habits. This guarantee says even when you are in the data set, it's data set X, still nobody will learn much about your flossing habits. So once you have this, you see that you automatically not just protect people, but you also get for free copyright protection. Think about a large language model that is built using differential privacy. If you can't tell whether an image was included or not, then you can't produce something that's very close to that image. So you automatically get copyright protection. Also, by understanding the roles of the epsilons and how they add up, we can handle multiple computations. And that gives us programmability, so we can program in a differentially private way. And it's beyond the scope of this talk, but you can also get safe data reuse. Okay. I don't have the time to tell you how we do this, but the way you should think about it is impressionist art. So, in the impressionist art, the details are blurred, but the truth of the image comes through. And that's essentially what's happening in differential privacy. I've talked to you about privacy, but there are other concerns. So another concern is fairness. And that's a much, much harder problem. So how can we learn from data without learning the biases contained in the data themselves? We think that people who are similar should be treated similarly. People who are similarly qualified for a loan should get similar decisions on their loan applications. People who are similarly qualified for college admission should see similar. But how do you define similarity? Who decides what similarity is? And how do you define and how do you measure similarity? That's a serious technical challenge, but it's also contextual. There's not going to be a one-size-fits-all answer. And another issue is editorial biases. Think about the large language models. There are only a handful of large language models that you have access to. And technology isn't neutral. There are editorial decisions that are made all the time. So should we really have 3 points of view as to what kinds of things people should see and hear from a language model? How are we going to address that? Think about, imagine if you were searching for a measles vaccine and you said, I need a measles vaccine, and Google just decided not to do an autocomplete, not to make any suggestions for you. And if you don't happen to spell vaccine correctly, maybe you won't get to your vaccine. This would be unconscionable. This is an example that I tried this morning. Google's behavior is not the same as that of DuckDuckGo and Bing, which both do the autocomplete. In 1912, the Titanic, with lifeboats to accommodate only about half of its 2,200 people on board, struck an iceberg and sank within hours. In the wake of this tragedy, international maritime safety laws were revised. So we have decisions to make. We can scale responsibly or irresponsibly, the way the Titanic did. We can have lifeboats sufficient for all on board or not. This is the stuff of regulation, just as with maritime safety. And government should protect the populace, and so we need to elect people who will do so. The choice has to be made democratically. Thank you.
Thank you very much. And I hope you've enjoyed your lunch. So this is going to be on there are no social overtones to this. This is just sort of getting science correct. We're getting the science that we learn from data correct. Okay? So just to remind you, if you missed this or if you missed this talk this morning, when I'm talking about learning from data, I'm extremely general. The paradigm is completely general. We have some learning algorithm or function or program. It's called F here. It takes data, it operates on the data. The data can be multimodal, unimodal, anything, and it produces outputs. So an output could be a recommendation system, a repayment predictor, it could be a chatbot, it could be something obtained like a location in the DNA that seems to be associated with COK. So, this is one of the ways we like to do science now. It's one of the driving paradigms now for science. And maybe some of you remember this famous paper from about 2005, Why Most Published Research Findings Are False. And that is going to sort of come from a misuse of data. And one way to think about this, and there's several ways it comes up, but one way to think about this is that we as humans have a tendency to see signal in what's actually just random noise. And there are many examples of this, constellations in the stars of the sky, for example. Here's one that comes from a famous probability book by Feller. Maybe if any of you have taken a probability class, you were probably lucky enough to use that book. It's a wonderful book. And he gives many examples there. One of them is the flying bomb hits, is what the caption says, on London during the Blitz in World War II. So people living in London, experiencing all of these bombings, believed that the bombings were clustered, and they wondered why were these particular locations being targeted? Because if it was clustered, there must have been a reason. So most people believed that the bombings were clustered. But in reality, that may not be the case. Maybe the bombs were just being dropped randomly on London, and people were seeing the signal when there was really noise.
And so what the statisticians did was they took a map of London where the bombings were, a map of London, and noted where the bombings were. And they covered the map with a grid of cells. I think it was 1/4 of a mile by 1/4 of a mile, so square cells. So here are the cells. And now, in each cell, they noted how many cells had 0 hits, how many had 1 hit, 2 hits, and so on up to 5 or greater. When I put the numbers there on the left, and I took this from Feller's book. Okay. And then, using sort of standard theory of random variables, they analyzed if the bombs had in fact just been dropped randomly and uniformly, what would we have expected to see? So for example, there were 229 cells with no hits, and the prediction, given the total number of bombs altogether, would be 226.74. So very close. How many cells had just 1 hit? 211, predicted 211.39. And so what you would expect to see if things were really random looked very much like what was actually seen. And so now people believe that the bombs were not clustered, that it was just randomness, and these apparent clusters were just little mini statistical flukes, or mini, yeah. Okay, so people see signals where there really are no signals. And it's understood that this is the case, and in data analysis and machine learning, AI, people go to great efforts to try to combat this. So, how many people here have heard of a holdout set? Yeah, hands please, I just want to get an idea of the audience. Okay, so good. So the general idea in a holdout set is the following. You take a big data sample, that's my big circle. You just randomly split the data elements, call some of that the training data, and call the remaining ones the holdout. You ignore the holdout for a moment, and you process the training data. You do whatever learning it is you want to do. You build the predictor you want to predict, or whatever. Then when you think you have something, and it's working really well on your training data, you want to know, does it actually work on the data as a whole, or not? So did it notice that sort of patterns that were local statistical flukes that wouldn't really apply at another random sample or not? So then you take this thing that you built and you go and you look at your holdout set and you run it on the holdout set and say, does it behave well there? If you built a predictor, say for loan repayment that works well on the training data, does it also work well on the holdout set? And because you haven't included the holdout set in your training, you can't possibly have steered your algorithm to sort of to the test of the training data. So that's one approach. Another approach is called, it's related, very related, it's called cross-validation techniques. So now you take your data, you split it up into, in this case, 4 chunks called folds for reasons that I don't know. And first you train on folds 2, 3, and 4, and you check, you're treating fold 1 as if it's a holdout set. And so you check it on fold 1. And then you train on fold 1, 3, and 4, and you check it on fold 2, and so on. So cross-validation is a big technique in machine learning. Has anybody heard of hypothesis testing? So let's say you designed a new drug, and you want to know, does your drug work well? So while working well has to be a relative term, and you want to think about, suppose your drug actually does nothing. What would you expect outcomes to be for people who are being treated with this drug? So you have to get your baseline straight. And the key point, and so your hypothesis is that the drug does nothing, and if the drug is really effective, you will, disprove that hypothesis. So this is how drugs are evaluated. And the mathematics behind it takes into account exactly the kind of things that the statisticians pointed out with the bombing in London. That there will be sort of natural fluctuations, even if something has a nice normal distribution. Again, flipping a coin that with probability 3/4 comes up heads, well, I'm not going to see 3/4 in
heads, if I fill it 10 times, I'm going to see something that's not too far from 3/4 end probably, but not too close either. And that's what this distribution is showing. There's a great math for that, but if you have many hypotheses and you're testing them all on the same data, you have a real problem that if your numbers are set to work to sort of screen out small statistical flukes, if you have enough things that you're testing, enough drugs that you're testing, some of those statistical flukes will be big, and you won't see it. It's still random noise, but you'll think it's real. So there's a whole theory developed for multiple hypothesis testing, and the famous Benjamin Hochberg-Q, BHQ algorithm, sort of said, hey, let's change the problem, and instead of trying to never rule out something that shouldn't be ruled out, and always rule in the things that should be ruled in, let's just change the goal and say, we're going to name a fraction Q, for example, in this case, 20%. And we are going to design an algorithm that will find mostly true outcomes and have a small number on average, just a Q fraction of them be false. And now we can run new tests and get new data and study these. So again, another sophisticated, beautiful technique for dealing with these missing from all of that literature is something that we call adaptivity in computer science, and the statisticians refer to as exploratory data analysis. And in adaptivity or exploratory data analysis, instead of sort of listing before you see your data what are your questions, you allow your questions to vary depending on the data and the outcomes, the answers to your earlier questions. You can think of it as a kind of drilling down and asking more and more specific targeted questions as you get preliminary answers. So again, in adaptivity, the choice of the new computation depends on the previous answers. So what can go wrong? Let's go back to our holdout set. Let's say you train your repayment predictor, okay? And you get it to the point where it works really well on the training data. And then you test it on the holdout set, and it's terrible. It turns out that you built a predictor that was just guided by idiosyncrasies in the training data. The holdout set is sort of fresh samples, you haven't seen them before, and it fails because it has different idiosyncrasies. So that's not a problem. You go back and you train another predictor. But now you do have an issue. And that is that the way you do your training when you've done it the second time is no longer independent of the holdout. The holdout set, in some sense, is no longer fresh data, because everything you've been done has now been affected by the holdout set. And so all of the math for explaining why using a holdout set works and gives you valid answers goes out the window. It doesn't work. My favorite example of the risks of adaptivity comes from something called Friedman's paradox. So I didn't want to actually use the language of linear regression and so on. So let's just sort of make up a story here that will give you the spirit of what Friedman found. Let's say, I love spicy food. So let's say, what are the things about people that allow us to predict whether or not they like spicy food? So, do they like to wear the color red? Do they have perfect pitch? How old are they? Are they wealthy or are they of modest means? And are their earlobes attached to their face or are they detached? And then for each person, you maybe write down how much they like to wear red, whether they have perfect pitch, and so on. And for each person, you also write down, yes, this person likes spicy foods, yes, no, yes, yes, no. Okay. So this is the kind of thing the kind of data that people work with in regression analyses. They try to find weights for these features of how much red you wear and perfect pitch and so on that will help them predict whether you like spicy foods. So what did Friedman do? First of all, he made up data, but every single piece of the data that he made up was independent and completely at random. So there is absolutely no statistical relationship between the features, the data that he wrote down, the features and the answers. So there's nothing to predict because there's nothing there, it's all random. But remember I said that you have some like little correlations, little statistical flukes? Well, so the next thing that people sometimes do is they say, okay, let's look at the various features and which ones seem to be even, just modestly correlated with the outcome. So you select those features that seem to be modestly correlated with the outcome, and now using only those features, you build a predictor. And your predictor is great on the training data, on the data set, and it's terrible on the population. So he showed that it would be great on the data set with like in 100 people and 50 features. It is great at the data set. You overfit because you chose features that by coincidence were just a little bit related to the outcome, correlated with the outcome. And then you said, let's only look at those features, and wow, we get super correlation. But of course, it's gotta be terrible on the population because there's no rhyme or reason in these data. They're just random noise. So this is a very interesting and natural statistical mistake. Like the novice doesn't realize that it's okay to choose a few features that seem correlated, but you can't test it now on the same data. You have to get fresh data. If you don't, you end up with this situation. So, great example. The problem is, consider any kind of real investigation, a real study of a medical data set, like the Framingham Heart Study, that people go to again and again and again. And they learn things, and they publish the results, and then people build on that, and they ask new, important questions based on that, and they study the results. It's the same data. Real science is an adaptive process. There's no getting around that. It's just how we operate. So, how do we get out of this conundrum? I used the term overfitting before. Let me be a little bit more precise, just a little. So overfitting, I want to say, is finding a pattern that is specific to the data set and does not extend to the general population. So the general population is the picture on the left, and the data set is the sample, and that's the piece on the right. I took a sample from the general population, plugged it down. And so, as I said, a statistic, earlier today, a statistic is a quantity computed from a sample, and we're going to look at questions of the form. What we're interested in is statistics about our population. What fraction of the population plays the viola? What fraction of the population speaks French? What fraction of the population likes to lift weights, and so on. Those are, we call those statistical queries, or fractional statistical queries. And we're going to make a conceptual leap now. We're going, because we want math that's going to work, whether the person who's analyzing the data is ignorant, educated just a little bit, but makes a silly mistake, like happened in Friedman's paradox, or is actually malicious. So the conceptual leap is, we're going to define something we call the accuracy adversary. This is a party that will interact with the data, and their entire goal in life is to find a statistic for which the data set is not representative of the population. So it's not enough for the statistic to exist, the adversary has to get its hands on it. So for example, here's what, I'm trying to introduce you to the way of thinking in my world. So I'm going to give an example which is clearly preposterous, but if your math doesn't rule out this example, who knows what else it fails to rule out. So here's my clearly preposterous example. The accuracy adversary maybe sees the data set S, and it defines the property to be is in S. So, what fraction of the population is in S? If we look at our picture on the left, the fraction of the population that's actually in the set S is very tiny. But on the right, the fraction of the population that is in the set S is 100%. Everybody in the data set S is in S. So clearly ridiculous example, but it's making a mathematical point. Moreover, of course, what this says is, if the accuracy adversary, whose entire job in life is to come up with a statistic for which the data set is not representative of the population, if that adversary can see S, it wins. It can do it. It defines the property to be simply is in S. So, seeing this situation, let's step back for a second. What is the point of training data? It's to teach us about the population from which the data are drawn in order to make predictions, correctly classify or identify things, suggest research hypotheses for future work. In overfitting, this learning process goes away, and predictions and classifiers that work well on the data set fail to generalize to the population as a whole. That means that all your effort was wasted. And another option is that it produces hypotheses that are of poor quality, and that means if you want to test those in the future, this is just wasting future effort. So again, the problem is that we're overfitting by kind of memorizing the details of the training data, and what we really wanted was to learn the general population trends. And of course, we have a way of learning about the population as a whole without learning about the individual data items in the sample. And that's what this morning talk was all about. So differential privacy says the outcome of any analysis is essentially equally likely, independent of whether any individual opts in or opts out of the data set. And what it ends up translating to is that the adversary can learn about the population as a whole without learning about the individual data items in the sample. Therefore, it can't overfit to those individual data items. And of course, there was this fundamental law that I mentioned in the morning that overly accurate estimates of too many statistics completely breaks privacy. So, of any kind, even before we thought of differential privacy, so that still applies. And this image here, again, is Monet's picture. So the gardens that you don't need. What differential privacy does intuitively is it sort of blurs the things that you learn. So you get the general picture without getting the details. Okay. So just trying to, I can't go through proving the theorem, but I can tell you a little bit of the intuition. So fix a statistic, say, what fraction of the population is over 6 feet tall? Now, almost all large data sets will give you an approximately correct reply. Almost all large enough samples will give you an approximately correct reply. And if you know central limit theorems, this is Chernoff's bound. So what this tells us is, for this fixed query, whatever it happened to be, I said 6 feet tall. It doesn't really matter which it was. Most data sets, a randomly chosen data set, is very likely to be representative of the population as a whole for this query. So now, suppose that in the process of adaptive exploration of the data set, the analyst finds a statistic for which the training is no longer representative of the population as a whole. That means that she has learned something specific to this data set, because as we saw for the first query where the data set doesn't even have to be chosen yet, almost all data sets will be good. So if she can get her hands on something for which the data set is not representative, then she must have learned something about the data set. It just doesn't happen by chance. Too unlikely to happen by chance. And the key technical insight has to do with what we call the post-processing property of differential privacy. So here I've sort of given a picture of the interaction. The data analyst asks one question, gets an answer. Based on that question and answer pair, she decides which her second question will be, gets an answer, and so on. And if the mechanism in the middle is always answering with differential privacy, this whole interaction will be differentially private. So the subsequent queries depend on the previous queries and answers. And if n ensures differential privacy, then what this means is that the ith query can't reveal too much about the data set. It can't be too closely correlated to the data set. So it's not going to be specific to the data set. So compare that with the killer query, which was, you see the data set and you design a query that's exactly that for that data set. Differential privacy rules that out, and a bunch of stuff in between. Okay, so that's kind of the theory. And so, you go off to the statisticians and the data analysts and you say, use differential privacy, and they say get lost. We want to do things the way we always have. Differential privacy gives you a worse accuracy, privacy, decreases your accuracy. We have to retrain, we don't know how to do this, and so on. So get lost. And so it turns out that, even with this, there really is something nice that we can do. We're going to modify the holdout that I described to you earlier and make it reusable. So I haven't had a chance to talk about it. I've said to you a couple of times that if you get overly accurate estimates of too many statistics, you ruin privacy. So implicit in all of that, buried in all of that, is that you can have what we call a privacy budget, which you can spend any way you want, but it's a way of tracking the worst case privacy loss that you could have experienced and stopping before it gets bad. So we're going to repeat the following steps until the privacy budget is exhausted, or we can repeat it until it's exhausted, or we just like what we've learned and we're happy. So the analyst can explore the training data exactly as the analyst did it all along. No privacy, no constraints, nothing. And let's say that our analyst comes up with some object, like a repayment predictor, which has been a running example. Could it be that? It could be a classifier and so on. And then she tests this predictor that she has built on the holdout set, but she does that step using differential privacy. So the holdout set is protected with differential privacy. And what that means is that actions taken, if it doesn't do well on the holdout set and the analyst goes back and retrains, the retraining is not very affected by the holdout set because the holdout set is protected by privacy. And so it truly becomes reusable. And sort of mathematically what's going on is you just sort of imagine that this training data are simply hardwired into a fatter adversary, and it's just this adversary against the holdout set, and all of the problems of adaptivity go away. So that's all I have to say about this, and it was a fun discovery.